A-Level Physics Lesson 57, all about kinetic energy and potential energy. Yes, in this lesson we're going to do some derivations. So you'll know that the kinetic energy equation, I'll just write this down, kinetic energy equation, you'll know that that is half mv squared. It was one of the equations that GCSE students are required to memorize. Yes, I know that students have been given the formulas in recent years due to supporting students who have been disadvantaged by the COVID-19 pandemic. And yes, those supporting changes are still there at the time of recording, even though the pandemic was 5 years ago. It is my hope that they remove it and students will have to remember things again, but okay, I'm a lone voice shouting out against those formula sheets, so now is not the forum for me to moan about it. Anyway, this is an equation that the specification says you should have memorized. At least you should have some familiarity with it. We're going to derive it, and there are lots of ways of deriving it. With students in my school, when I do induction lessons, when they're still in year 11 to see whether they want to do A-level physics or not, I actually derive kinetic energy in 3 or 4 different ways as part of that lesson. I might record that because it's a fun little lesson, but it does get progressively more complicated as we go through. The problem is the way that I'm going to derive it uses a Suvat equation, and as we've already met, the Suvat equations assume that the acceleration is constant. But this equation for kinetic energy works whether the Suvat equation, whether the acceleration is constant or not. So we're going to start the derivation. We're going to start the derivation with the idea of work done. So remember that work done is equal to F times S. And I'm just going to write it like that. I'm not going to bother with the vector stuff, although it's all there somewhere. I'm not going to bother with that. I'm just going to write it like this. F times S. Now remember that F is ma. So we could write this as m times a times by s. So we've got acceleration times by displacement right there. Fine, okay. Well, what is acceleration? Is there another way that we can define acceleration? Oh, yes, there is. We can write down that our acceleration is from a Suvat equation v minus u divided by t, and if the initial velocity is equal to 0, then our a is just going to be equal to v divided by t. And we'll use that in a second. We also have s, the displacement. Now that's equal to, according to another Suvat equation, half times u plus v, this is the definition of average velocity, multiplied by t. Okay, but again, we've said if u is equal to 0, so that all of the work that is done is the kinetic energy store of the body, so we say the initial velocity is 0, then this just becomes s is equal to 1/2 times by v times by t. And now we can plug both of those equations into there. And when we do that, we get that the work done on our body is equal to the mass multiplied by a over t and multiplied by 1/2 v times by t. I don't know, a over t, I meant v over t. I must have got distracted momentarily. A is v over t if u is equal to 0 and a is constant. Right, there we go. I might even put these little crosses in there, even though they're not cross products, just because it makes it easier for people to follow the derivation. The t's will cancel. We've got 2 v's there. So that's just 1/2 times by mass times by v squared. But that derivation has some limitations. Because it used Suvat equations, only works for constant acceleration, which is not true for the acceleration, for the kinetic energy equation. That's not a limitation of the kinetic energy equation, but I'll leave it as this derivation, and if I get round to recording the video I was talking about with lots of different stages in the derivation, lots of more complex derivations where one by one we remove the parameters, the limitations, the assumptions that go into the derivation, like this one, the assumption was A is constant. If we remove that, I'll record that video at some later point. Right, now let's talk about gravitational potential energy. Gravitational potential energy equation. Did I use the word energy? Yeah, I'm trying to keep the same energy equation. I'm trying to keep the same notation as I did for the kinetic energy equation before. I believe I underlined it, so I shall do the same. And we're going to start from work done again. We're going to start from work done. There are some issues with this equation as well, and we'll get to them when we do gravitational fields later on. This is a starting point, so derivation, the equation first. That's what I did last time, wasn't I? I stated the equation, then I said the derivation. So E is equal to m times g. Now, we usually just write h, but I'm going to put delta h here to make it so it's not quite so wrong. Still wrong, but it's not quite so wrong when we get to gravitational fields later on. So the derivation of this equation, once again, we're going to start from the work done, is equal to the force multiplied by the displacement. And this time, the force is the force of gravity. So we're going to say the force of gravity is equal to mg. And we're going to say that the displacement of the object, if we're lifting the object up, that is the difference in height of that object. It has been displaced through a certain amount as we've lifted it up. Well, the equation's pretty much done. It's not much of a derivation. It's just m times g times delta h. I don't know what else to say. It's just it comes out like that. So there we go. Derivation of potential energy of gravitational potential energy due to its position in a gravitational field. There it is. So all we have to do is be able to use these two equations together. If we have a situation where these are the only two energy stores, so for example, there's a roller coaster. Let's go with example, and I'll try and draw a diagram. So let's go with a nice example of where we use them both together. A roller coaster. Can I make my pen thicker? Oh yeah. So let's have a roller coaster that starts there, it goes up, and then it goes down again. And maybe it goes up into a loop, and we can play with that loop. It's an awful loop. Let's try that again. It goes up. I don't know why I'm fussing with this so much, but I want it to look good. It goes down into a loop. No, that's a slightly less terrible loop. Right, okay. There's our roller coaster, and we'll label it. Let's just stop it. I'm trying to change the pen size back to 0.6. Oh, that's too small. 0.6. We'll label it roller coaster. So the way a roller coaster works is we transfer energy to lift up our mass, and then that energy, we don't put any more energy in. That energy just shifts between the two stores, the kinetic energy store and the gravitational potential energy store. So to lift the car from there to there, we have to have a certain amount of energy that we put in. And that's going to be equal to There's our difference in height, like that. And so if that's our difference in height, then the energy stored in our roller coaster is going to be the gravitational potential energy, which will be m times g times delta h. And we'll say that it has, let's say, no kinetic energy at the top. Now, obviously, that's impossible because then it wouldn't be able to roll off. It's got to be moving. But let's say it's 0 at the top. Then by the time the roller coaster gets down to here again, it's dropped through that height, h. And at this point, we have our potential energy equal to, let's say, nothing. And our kinetic energy is equal to a half mv squared. But importantly, the total energy here is equal to the sum of the two. So we're ignoring friction transferring energy into the thermal energy stores. This is still true here. EK plus EP is equal to E total. That's still true. So we've got the total amount of energy does not change. It's still the total amount of energy. So what does that mean? Well, that means we can combine those two equations, and we can say that the mg delta h that it had at the beginning must be equal to the half mv squared that it had at the bottom. And of course, as it moves around this track, we could calculate how much energy it has in each store when it gets to here. So this is some new height above the ground. What shall I call this? I don't know what letter to use for this. I'm just going to use S. Doesn't really matter. Like this. So when we are at the top here, our gravitational potential energy is mgs, but our kinetic energy is going to be what we had before, which is mg delta h, subtract mgs, just like that. But we also can say that those two added together are still equal to, so ET is still equal to the total amount of energy that we have, because energy is conserved. So now our equation starts looking like, where is it? So total energy is still the same as what it was. So mg delta h is going to be equal to our potential energy, mgs, plus our kinetic energy, half m, well now it's v squared. And so we can use that to calculate what our new v is, if we wanted to. We could say, right, okay, well, v is going to be equal to 2 lots of mg delta h minus s divided by m. Oh, the m's cancel. There we are. It doesn't actually depend on m. Under the square root. There we go. So I derived that from that equation. So we can work out the speed of the roller coaster car at that point just by saying that the total energy hasn't changed, and it's related to the difference in heights between the height it dropped from originally and the height it's gone back up to. Obviously, the bigger S is, the smaller V will be. So we can play with these sorts of equations like this as much as we want, and it depends on the situation that we are given as to which of these equations we manipulate and how we manipulate it. That's just using algebra to solve problems, and I can't really teach that in videos like this. That's something you have to practice to get better at. So I will stop there. That is our derivation of two different energy stores and a quick review of, look, this is how you would use it. You'd say the total energy is fixed. We just shuffle energy from one store to another. And that's all I'll say about that. I hope you found that useful, and I hope that you will join me in the next video. Do you know what? While I'm doing this, I might as well just actually say V equals, I can't help myself, 2 times g times delta h under the square root. There we go. Ha! Now I'm happy. Now there's some sort of continuation. Right, I'm done. I'll see you next lesson. Bye-bye.